Just recapping what we saw on the previous video where we introduced exponential family. We said that everything in the exponential family had a canonical form, so a natural parameter that we can define for the distribution. So in this case, when I'd written it in this form of a of x times b of theta times the exponential of c of theta times d of x, theta is the parameter, x is the variable, then whatever my c of theta is could be considered the natural parameter for the distribution. Now, one reason that we do that is that when we've written it in the exponential form with this natural parameter, I've got some easy calculations that I can do to generalize some properties of the distribution. So if I've got it in this form, then, well, I know that the integral, I've written integral here, it would be summation, of course, if it were discrete, but the same argument holds. If I want to integrate the density function, that has to be 1. I'm integrating with respect to x, so b of the natural parameter can just pull outside the front. So now if I differentiate this with respect to c, I'm basically differentiating 1 with respect to c. The rate of change of 1 doesn't tend to change very much, it tends to change 0. What this does mean is if I actually do the derivative on the left, then differentiating b of c times this integral will give me b dashed of c times this integral plus b of c times the derivative of this integral. Now, I've maybe been a bit slack pulling the derivative through the integral sign, or at least justifying that, but those two things have to sum to 0. Now, what that means is the little bit of rearrangement, division by b of c. And what I will get to is I will soon get to the fact that the derivative of the natural log of b of c, because of course the derivative of the natural log of b of c will be b dashed of c divided by b of c. The integral of f of x with respect to x is 1. And the other term I've got there is just the integral of d of x times f of x. So is the expectation of d of x. Those have to sum to 0. So what it does tell me is that the expected value of d of x can be calculated just by differentiating log of b of c and taking the negative of that. So in many cases, d of x will have some nice tidy form, say d of x is x, as it is for many distributions, in which case the expected value of the variable is just the negative of derivative of log of b of c. As we saw in the first video on the exponential family, I can write the Poisson distribution in the exponential family form of 1 on q factorial times e to the minus lambda times the exponential of q times log lambda. And this tells us that the natural parameter is setting c as the natural parameter equal to log of lambda. So previously my b term was b of lambda is e to the minus lambda. If c is the log of lambda, then lambda is e to the c. So e to the minus lambda becomes e to the minus e to the c. So what we saw to calculate the mean was if I wanted to know the exponential, so the expectation of d of my variable. D of my variable was just my variable, so in this case, the expectation of q will just be the negative of the gradient of log of b of c. Well, taking the log of e to the minus e to the c will just give me minus e to the c. So the negative of that differentiated is just the gradient of e to the c with respect to c, which is e to the c, which is lambda. So this tells me that the expectation of a Poisson variable is its own rate parameter, lambda, which is correct. We can also do the same for the variance, or do something similar. It's a little bit messy, but by similar arguments, I won't go into it in the same level of detail. But in the same way as I could get the expectation of d of the variable, I can get the variance of d of the variable, and in this case, I don't just have to differentiate log of b of the natural parameter once, I have to differentiate it twice. But again, the variance is just the negative of the second derivative with respect to the natural parameter of log of b of the natural parameter. So again, likewise with the Poisson variable, it's a super easy calculation, because instead of differentiating e to the c once, I'm differentiating e to the c twice with respect to c, and this confirms again that the variance is equal to the expectation, is equal to e to the c, is equal to lambda. We already saw the example of the binomial variable, at least where n was known, and hence it was in the exponential family. And when we wrote it in the exponential family, what we saw was that the natural parameter c, in this case c of the parameter p, was just the log odds ratio, so log of p over 1 minus p. And when I wrote it in this form, I'd have the function of x being n factorial over x factorial n minus x factorial. Then I'd have my function of p being 1 minus p all to the n. But when I put it in terms of the natural parameter, that became 1 minus e to the c all to the n. So I want to work out the mean and the variance. Well, I'm just differentiating this with respect to c and negating. So the derivative of log of 1 minus e to the c all to the n will give me minus n over times minus e to the c over 1 minus e to the c, which will just simplify to np, which I know is the expectation of the binomial. And the variance is basically no harder than that, just differentiating again e to the c over 1 minus e to the c with respect to c. And in this case, a little bit more calculation. But what I'm going to be left with is exactly what I would expect of np 1 minus p. Now that's actually easier than working out the variance directly in terms of summing binomial coefficients. So it does actually give us this nice framework that whatever the distribution, if I can show it in the exponential family, I have these nice ready-made calculation tools for the mean and for the variance.